All right, and we're back with 9.3. This is one of my faves, one of our last new units or properties, Gibbs free energy, and talking more about this idea of thermodynamic favorability. So those of you who took advanced bio with Francis should be familiar with Gibbs free energy. Those of you who did not, it'll be brand new. But what we're talking about are reactions that are spontaneous or thermodynamically favorable and reactions that are non-spontaneous. So not just the boring reactions that aren't spontaneous, but what does this really mean in chemistry? Well, if a reaction occurs readily, we call it spontaneous. It doesn't mean it's quick, but that it will occur without any added energy. So I don't have to force the reaction to happen. It'll already be happening. The universe just likes that reaction happening. And this is another way to say spontaneous is thermodynamically favorable. You'll also find that this term is more commonly used now in AP resources, but if you look at older ones, they might say spontaneous. But we tend to like the term thermodynamically favorable more because it gets across, it isn't just fast, right? We see spontaneous and we think that means it's really fast, but that's not necessarily what it means. And then obviously the inverse is something non-spontaneous or thermodynamically unfavorable. So here are some examples. Something that is really thermodynamically favorable, the combustion of hydrocarbons. That means you add a tiny little spark to, say, a piece of paper, and it's going to light on fire. You don't have to do really much more than that little spark. The universe likes things burning, right? Sometimes things are spontaneous, thermodynamically favorable, dependent on the temperature. So like water freezes, right? If water is at negative 10 degrees Celsius, it's going to freeze, right? Pretty readily. But if it's at 30 degrees Celsius on a hot summer day, it's probably not going to freeze that quickly. Okay, so that's thermodynamically or temperature dependent thermodynamic favorability. And then something that's totally non-spontaneous. Water molecules do not readily break apart into H2 and O2 gas. If they did do this, well, the universe would look very different, but our bodies probably would not be 70% water. We would probably have not evolved if that happened, just readily at room temperature. So thank God for that. So what does this mean? Why does the universe want a thermodynamically favorable reaction? So there are two things to consider: the enthalpy, so the delta H of the reaction, as well as the entropy, the delta S of the reaction. So the universe is lazy and doesn't want to have to put energy in. It wants energy to be released. It wants enthalpy to be released. So universe thermodynamic favorability wants a negative delta H. It wants something exothermic. Right? So the universe is lazy. It likes when things are exothermic. It doesn't want an endo. In addition, the universe is a pretty messy place. I don't know if you've looked around lately. So the universe does not like really heavily ordered stuff, does not like organizing. It wants entropy to increase, meaning delta S is going to be positive in a thermodynamically favorable reaction. So these two things, a negative delta H and a positive delta S, the universe loves those things. I'm really lazy and I'm really messy. Maybe some of you can relate. Okay. So some things, like I've already talked about, tend to be spontaneous if they're exothermic. So here are two examples. We've got solid water melting into liquid water and liquid water freezing to turn back into solid. You can see that these are spontaneous, aka thermodynamically favorable, dependent on the temperature, and we'll see why in just a little bit. But ice melting into liquid water is thermodynamically favorable above 0 Celsius. We get this increase in entropy, which we like, but it is endothermic, right? We have to add energy into the system in order to melt it. So that kind of counters. But we also see the reverse is true. When we're below 0 Celsius, when liquid water freezes, it actually releases energy, right? This is exothermic, so we like that. We like this negative delta H, but the entropy decreases, right? These molecules are more packed together when they're turning into a solid, whereas they're a little more floaty, movey abouty, a little more random in liquid water. So as we can see here, a temperature reading is important in determining the thermodynamic favorability of a reaction. So this is a lot of qualitative stuff, but we can put it into a quantitative form through this thing called Gibbs free energy. So ultimately, this is a quantitative property, and we call it delta G, and it incorporates the enthalpy, so the delta H of a reaction, the entropy, the delta S, and the temperature that a system or a process is at to determine will this actually be favorable based on the thermodynamics of the system. So sometimes you'll see delta G described as the energy of a system available to do work, right? So what energy is available to do work depends on how much heat is released, how much heat is like out there when this reaction proceeds, but also how scattered about are the particles. If the particles are all packed in, right, really low entropy, there's not a lot of available particles out there to do work. And when we talk about work, this is in the physics setting. We're not going to get into what work really is in this class, but take some more physics, you'll learn about it. So we have to relate enthalpy, entropy, and temperature to delta G. How do we do that? One of my favorite equations. Oh, and the formatting looks bad. Okay, it looks like this. I'm sorry, guys. Looks like delta G equals delta H minus T delta S. I also like to call this agatas. Agatas. Yeah. Okay, so when delta G is a negative value, the reaction is thermodynamically favorable, spontaneous, regardless of temperature. Or sorry, I said that wrong. If delta G is a negative value regardless of the temperature I plug in, that reaction is spontaneous at all temperatures. If we are negative for delta G only at certain temperatures, then we are temperature dependent. And if delta G is a positive value, the reaction is not spontaneous. It is not thermodynamically favorable if it's that regardless of temperature. So why does this actually matter? It determines, why does temperature matter? Determines what sign delta G would actually have. So here are a couple examples, and we're just going to practice plugging these in and looking algebraically what sign of delta G they would give us. And again, if delta G is negative, that means thermodynamically favorable or spontaneous. And if delta G is positive, that means we're going to have a non-thermodynamically favorable or thermo-unfavorable. So looking at these examples, all we're given is the value and sign of the delta H and delta S. So I'm just going to plug each of these in and we'll sort of look at what we get. So if delta H is a negative, okay, and we're looking at this one, and delta S is a negative, okay, negative. Well, regardless of what the temperature is, I'm going to have negative temperature times a negative. So negative temperature times a negative, and then negative delta H. So a negative number minus another negative number multiplied by that. So this is going to be a positive term, right? This is going to look like a negative number plus something positive, right? The negative sign times the negative of the delta S. So this is maybe going to give us a negative, maybe going to give us a positive for delta G. This is temperature dependent, okay? And the reason is, depending on how big T is, right, this might be a really big positive number and it outweighs the negative. But if the temperature is really, really small, then this positive might not outweigh the negative and we still end up with a negative delta G, okay? All right, let's look at this next example. So when we have positive delta H and a positive delta S, what do we get? Whoop, what happened there? Yoink, yoink, yoink. So positive, positive. So I've got a positive delta H, positive delta S, and my temperature, right? Well, what I'm going to get is this positive number minus another positive number, right? Temperature times delta S is going to give us a positive number, but I'm subtracting that. Okay, so again, I get a situation where it depends on how big the temperature is, right? If temperature is huge, well, then I'm going to subtract a bigger number than delta H is and end up with a negative over here. But if my temperature is really, really small, I'm going to have a positive minus a small positive number. So I'm going to end up with another positive over here. But it really just depends on the size of the temperature. So again, we get something that is temperature dependent. Okay, now we see this last example, which we've got a positive delta H and a negative delta S. The universe does not want to add energy, and it does not want entropy to decrease. So what do we get if this is positive and this is a negative value? Well, we get positive minus, and then, let's see, or sorry, yeah, the minus t times the negative is going to give us a positive, right? The minuses cancel out. So this is always going to give us a positive value for delta G. So this is non-spontaneous at all temperatures. So the only example I didn't give you is when we have a negative delta H and a positive delta S. So I'll just tack that in here. If delta H is negative and delta S is positive, that is spontaneous at all temperatures. So I didn't give you that example, but if those were the signs, we would see that. And again, that's exothermic and entropy increases. We really like that. Okay, so this is a table that shows you the relationships between delta H, delta S, and delta G. Again, this delta G tells us, does the reaction have thermodynamic favorability? If delta G is less than 0 at that temperature and set of conditions, it is thermodynamically favorable when delta G is less than 0. So you don't really have to memorize these, right? You do not. But just like I was doing, you can plug in placeholder values into Agatas and determine what the sign of delta G is going to be. And sometimes we're given actual values and you can plug them in. Now, this stuff is a little bit weird, but Gibbs is a state function. So we talked about this a little with delta H. It means it doesn't matter if you have a multi-step reaction. It doesn't matter how many steps it takes to go from A to B, from reactants to products. The delta G of the whole reaction is what it is. The path doesn't matter, okay? Now, how we actually calculate delta G, because of that, just depends on what's the delta G of formation for our products, just like we did with delta S and delta H, minus the sum of what are the delta G's of formation for our reactants. And again, this is going to be the same products minus reactants thing we've done for previous ones. Now, if you want, you can definitely look at this example question. Tyler DeWitt, the absolute GOAT of online chemistry education. You can pause the video, look at this link. It's a pretty quick video, but I'm going to do my own examples, okay? So here is one. We are given the delta G's of formation for all these substances. We're going to calculate the value for delta G and determine if the reaction is overall thermodynamically favorable. So before I get started, I'm going to say, all right, this means delta G would be negative, or delta G is less than 0 if it's favorable. So delta G for the reaction is the sum of the delta G's of my products minus the sum of the delta G for my reactants. And just like with delta H and delta S, I've got to take into account the coefficients as well. So looking at my products, I've got 2 N2s. Hey, that's 0, easy. So I'll just write 0. I've got 4 CO2s, that's negative 394. So 4 carbon dioxides times negative 394.4, oops, 0.4. And then I've got 2 H2Os, which are negative 2 times negative 237.2. All right, those are my products. My reactants are next. I've got 5 O2s, and hey, that's 0. Boom. Let's write 0. And then 4 HCNs, which are positive 121. Okay, so we would add those up, and I didn't bring my calculator. Sorry, guys. And that's going to give us the overall delta G. Now, I can already tell that this is going to be negative, but we'll just go ahead and get a value for it. Minus It's 237.2 minus 4 times 121. We end up with a really large value, negative 2536 kilojoules per mole. So that's the value of delta G. And yes, the reaction is thermodynamically favorable because delta G is less than 0. Delta G is a negative number. Okay. So do we want to pause there? No, I'll go ahead and go through 9.4. So when we talk about the thermodynamic favorability of something, right, I used that word spontaneous and then walked it back, said this doesn't mean the reaction happens fast, right? So even if something is thermodynamically favorable, the universe wants it to happen, it still might not happen quickly. We might not even observe it to happen at all at room temperature, even if it is mostly favorable. And that's because of this thing called kinetic control. So we've already talked about kinetics, but kinetics control how fast a reaction takes place. And recall that the kinetics of a reaction do depend on how many steps it takes to get from A to B. Kinetics are not a state function, right? The rate of the reaction does depend on the path taken. So let's recap this a little bit. We've got this Agathos relationship where a negative delta H and a positive delta S will always give us a negative delta G, aka something thermodynamically favorable. So like this guy. But we've also got these other three scenarios. Again, you can just plug placeholder signs into Agathos and get an idea of what delta G you'll get. You don't really need to memorize these. So as I was saying, sometimes thermodynamically favorable reactions don't seem to occur. And again, it's a state function, delta G. So we do not have any account of things like reaction pathways, activation energy, the collisions, what catalysts are there or are there not catalysts. This is kinetics. So I really love this diagram. It's a reaction profile showing Gibbs free energy on the y-axis with reaction progress on the x-axis. And we see the difference between products and reactants as delta G. Thermodynamics tells us, will it occur? Does the universe want this reaction to happen at all without added input? But the kinetics, this is that middle area, right? This is where it does matter what kind of a hill I'm trying to jump over. This just tells me how fast will it occur if it does, okay? So we'll look at a couple examples of what kinetic control does, or what causes kinetic control. So things we're looking at, when do you have a negative delta G, but it doesn't seem to occur on its own? Could be you have a really high activation energy. Could be the orientations molecules have to take are not super favorable, or they're kind of specific. Or you have a lot of particles that have to simultaneously collide in order for this reaction to take place. And the best example I have of this is burning wood, right? So I mentioned this earlier. Burning wood, combustion of any hydrocarbon, very thermodynamically favorable, right? If you start a bonfire, when it gets going, it's going, right? The universe likes that reaction happening. It's really exothermic, right? Releases a lot of heat. That's why we burn wood. It also increases in entropy. You get tons more moles of products than you have moles of reactants. But wood doesn't, like, out of nowhere just light on fire, right? It needs a spark. And that spark is a really high activation energy. So, burning wood, it might look like this, where we've got this really high reactants and this really low products, but we might have an activation energy that's like way up here, right? That spark is really big. And if that's a really big hill, that means the reaction isn't happening very fast until I supply that activation energy, and then whoosh, all the other molecules around getting that excess heat from the exothermic reaction, they're now able to get over the hump and react too. So I'll let you just pause this and read this question real quick. So, excuse me. Man, I'm really trying to one-take these video lectures, but it's a slog. Okay, so we have an exothermic reaction, and we're given the chemical equation. We're asked what's the sign for delta S and delta H. We know the sign for delta H is negative because we're told it's exothermic. How do we know that delta S is positive? Well, recall what we did in 9.1, right? If I look at this equation on the whole, I've got 2 moles of gas on the left, and I've got 3 moles of gas on the right. So more particles on the right means entropy increases as the reaction proceeds. That's a terrible arrow. You get it. It's an up arrow as reaction proceeds. Okay, so the question is then, when will delta G be negative, right? And we can just look at our agatas and just confirm, does that actually make sense? Well, when delta H is a negative value and delta S is a positive value, you get a negative minus T times a positive. So negative minus a positive number is just going to be an even bigger negative number. So it's always going to be a negative delta G, meaning it's always thermodynamically favorable. However, here's question 4. It doesn't seem to proceed at room temp. What could we do to the conditions to make it proceed? Well, this right here suggests to me we are at kinetic control, or the reaction is under kinetic control. The thermodynamics are all there. The reaction or the universe wants this reaction to happen. However, the kinetics of the reaction say it's not going to happen very quickly, right? So the answer here is increase the temperature, give them more energy, or use a catalyst, decrease the activation energy. But I'm also noting you could say anything that generally increases the rate of that forward reaction. So increasing the concentration of a reactant, increasing their surface area, or like is mentioned in red here, you could add a catalyst that lowers activation energy. You could increase the temperature of everything, make the particles move more so they collide more. That's going to help it move a little faster. And yeah, I think that's where we're going to stop. Sorry that was a little long, but wanted to combine those two topics together. All right, on to 9.5 next.